Okay, today we'll be talking about Chapter 2, and we're going to start by considering an experiment. If we have an Erlenmeyer flask filled with oxygen gas, and inside also is some steel wool, and we take a magnifying glass, concentrate the sun's energy on the steel wool, and get the steel wool to burn. The question is, will the mass of the flask and the contents change if the steel wool becomes ignited and starts to burn? Now, you can do this experiment or any experiment in a sealed system, and you will find out that just because a chemical reaction happens, if the system is sealed against loss of gases, for example, then the mass does not change. And the person who worked that out and worked out a theory of combustion, and really the person who first understood, in fact named oxygen, was Antoine Lavoisier. And his idea was codified in the law of conservation of mass. The mass of a closed system will not change regardless of the chemical processes occurring within. So matter, the atoms involved, is neither created nor destroyed in a chemical process. The atoms are simply rearranged. And because it's the atoms that have mass, you will not see a change in mass because you're not destroying atoms or creating atoms. You're simply rearranging the way they're hooked up. Now let's discuss another experiment. Say we have pure sodium chloride from seawater, and we have 53 grams of it. Somehow we're able to separate the sodium and the chlorine, and we're able to measure the grams of sodium, the grams of chlorine, and we get 20.9 grams of sodium and 32.1 grams of chlorine. We go to some salt deposits and we extract pure sodium chloride from it, 77 grams of it. We work it up the same way, separate the sodium from the chlorine. We have 30.3 grams of sodium, 46.7 grams of chlorine. So what I want you to do for each one of these cases is to figure out the percent by mass, in other words, the percent by grams, of sodium and of chlorine in each one of the cases. Put your playback on pause and do the calculation, and then we'll come back and discuss it. Okay, to calculate percent, we take one part of what we're talking about, and since we're doing mass percent, we're talking about a unit of grams. Take one part and divide it by the total grams times 100, and that gives us the percentage of each of the elements. So for the percent sodium, 20.9 grams of sodium divided by the total mass, 20.9 grams of sodium and 32.1 grams of chlorine, times 100, we get 39.4% sodium. And if we do the same for the chlorine, we get 60.6% chlorine. And of course these add up to what? 100%. So that, on the first case, is the percentage of sodium and chlorine in the 53 grams of pure sodium chloride. Now, we can work out and do exactly the same kind of calculation for the 77 grams of pure sodium chloride. And guess what? We get exactly the same percentage of sodium and of chlorine. In fact, as long as we're talking about pure sodium chloride, no matter where we get it, no matter how we purify it, if it's pure sodium chloride, it's always going to be 39.4% sodium and 60.6% chlorine. Now all this was observed by Proust, who formulated it into a law of definite proportions. And that is that a pure substance will always be made up of the same elements in the same proportion by mass. Law of definite proportions. So far we have law of conservation of mass by Lavoisier. The second, law of definite proportions by Proust. There's one more major law in chemistry, and that is the observation carbon. It can combine with oxygen in two ways to make two different compounds. For example, you can have 12 grams of carbon react with 16 grams of oxygen to make 28 grams of carbon monoxide. That's the very toxic gas resulting from incomplete combustion of carbon. Or you can have 12 grams of carbon reacting with 32 grams of oxygen to get 44 grams of carbon dioxide. If we compare the mass of the oxygen while the carbon is at 12 grams in each one of the situations, what do we see here? 16, 32. You see that that is a whole number relationship? Do you see that that's a 1 to 2 relationship? That is an example of the law of multiple proportions. It's a little bit more complicated to state this law than the others and to understand it, so we'll spend a little more time with it. John Dalton formulated this law. When two elements, let's call them A and B, form two different compounds together, the masses of B that combine with 1 gram of A can be expressed as a ratio of small whole numbers. Let's use an analogy of bolts and nuts to represent atoms that combine to form a compound. With compound X, 1 bolt reacts with 1 nut to form a compound Bn. The bolt weighs 7 grams, the nut weighs 2 grams, the compound X weighs 9 grams. But our atoms of bolts and nuts can interact another way if 1 bolt interacts with 2 nuts. In this compound, 7 grams of bolt reacts with 4 grams of nuts, exactly 2 times the mass of nuts that the first compound had. 2 grams, 4 grams. Because bolts and nuts interact with each other in small whole number relationships, 1 to 1, 1 to 2, etc., the mass ratio of nuts in the two compounds must reflect that fact. The mass ratio of nuts in the two compounds has to be a small whole number relationship if the mass of bolts is held constant in the two compounds. Dividing the grams of nuts by the grams of bolts in each compound gives us the grams of nuts per 1 gram of bolt in each compound. Then, dividing the larger of these two numbers by the smaller gives us a small whole number relationship, in this case 2 to 1. And this is consistent with the law of multiple proportions. The ratio of nuts per 1 gram of bolt in these two compounds is a small whole number. So here's a problem we can do, similar to this bolt-nut problem, but with real substances. The ratio of oxygen to carbon by mass in carbon monoxide is 1.33 to 1. Find the formula of an oxide of carbon in which the ratio of mass of oxygen to carbon is 2 to 1. So how would that look? Well, we have to make up our ratio here. We make a ratio of oxygen to carbon by mass in compound X, and that is a 2 to 1 relationship right from the question here. In the denominator, we also have a mass ratio of oxygen to carbon, and that's the given 1.33 grams of oxygen to 1 gram of carbon in the compound carbon monoxide. When we're done and work this out, we get a ratio of 1.5 to 1. And we can write the formula out as carbon 1, oxygen 1.5. But here's the thing. You're never going to have a half an atom of oxygen. You're going to either have one oxygen or two or three, etc. You're going to have a whole number of oxygen atoms because in compounds, atoms aren't split. Well, there's going to be a multiplier. If you multiply each one of these terms by 2, you will now have a 2 to 3 relationship. And that is the formula of the oxide of carbon, which has a ratio of mass of oxygen to carbon of 2 to 1. So now we have 3 laws that are the foundation of the atomic theory that, again, Dalton came up with. The law of conservation of mass, the law of definite proportions, and the law of multiple proportions. All 3 of those support the idea that matter is made up of tiny, indivisible particles called atoms, that all the atoms of a given element are identical, which isn't exactly true. We'll learn about that a little bit later. But all the atoms of a given element are not identical. But Dalton would have had no way to know that. Chemical compounds are formed when atoms of different elements combine. A given compound always has the same relative numbers and types of atoms. Chemical reactions involve the reorganization of atoms, changes in the way that they are bound together. We're going to start talking about particles of the atom, and before we do that, we need to review electrical charge. This is pretty basic stuff, and you probably have had this in high school or even grade school. There are 2 kinds of charge, positive charge and negative charge. And of course, we're talking about electrical charge. And we know that if 2 objects have different electrical charge, one is negative and one is positive, that they are attracted to each other. But if 2 objects have the same electrical charge, they repel each other. And to be neutral, something must have no charge or equal amounts of opposite charges. So that is what we're going to actually have someone prove in class. We'll have equipment in class, and a student group will be selected to come up and demonstrate these propositions here. Now let's talk about one of the first experiments that indicated there were subatomic particles, particles within each atom. The first is Thomson's experiment with what he called the cathode ray tube. What he did is to take a metal, connect it to a power supply, the negative side of a power supply, and then on another metal at the far end, he had a positive charge placed on it and a fluorescent coating that would show any kind of bombardment with a particle. When he turned on the power supply, particles seemed to be generated from the cathode and went and smashed into the anode because he would see flashes of light on the anode. What he did next was to try and figure out the nature of this ray that was being shot from the cathode to the anode. And what he did was to put electrical plates that were charged, one plate which was positive, another plate electrically charged negatively. And what he found is that these cathode rays were attracted to the positive plate. So, negative particles released from the cathode and shoots toward the anode. Particles deflected toward the positive electrical field away from the negative field. The amount of deflection inversely proportional to the mass of the particle. And this experiment gave what is called a charge to mass ratio for these particles. So Thomson was able to summarize his results as follows. The cathode rays are made of tiny particles, and these particles have a negative charge because they are attracted to a positive plate. The amount of deflection of these particles was related to 2 factors, the charge on each particle and the mass of the particle. Now, every material that was used to generate these cathode rays, every material at the cathode site generated the same numbers. So it was independent of the element that was being used as a cathode. And this indicated to Thomson that he was dealing with a fundamental particle of the atom, a particle that was common to all atoms, a building block, if you will, of the atom. And he calculated the charge to mass ratio of these particles was minus 1.76 times 10 to the 8 coulombs per gram, minus because the charge was negative. Now if you take a hydrogen atom and strip it of its electron, it becomes a hydrogen ion. And do a similar experiment with it, you can find its charge to mass ratio to be positive 9.58 times 10 to the 4 coulombs per gram. So Thomson concluded that if the particle has the same amount of charge as a hydrogen ion, then it has to have a mass almost 2,000 times smaller than hydrogen atoms. That the mass of these subatomic particles is very, very small. And later experiments by Millikan show that the particle did have the same amount of charge as the hydrogen ion. Secondly, the only way for this to be true is if these particles were pieces of the atom, building blocks of the atom. So apparently, the atom is not unbreakable. Thomson believed that these particles were therefore the ultimate building blocks of matter, and he called these cathode ray particles electrons. The next experiment on the electrical nature of matter was done by Millikan in a famous oil drop experiment. And he was able, from this experiment, to determine the charge of the electron minus 1.60 times 10 to the minus 19 coulombs. The way he did it is to atomize some oil and spray it into a chamber. The oil droplets drifted downward through a tiny hole and were then bombarded with X-rays, which resulted in the particles gaining a negative charge, which could then be manipulated to learn about them. Here's a video that shows this.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
So if the oil drop experiment gave the charge of the electron minus 1.6 times 10 to the minus 19, and Thomson's experiment gave the charge to mass ratio of the electron as minus 1.76 times 10 to the 8 coulombs per gram, how can you use these numbers to calculate grams of the electron? How many grams does one electron weigh? Pause your playback and do the problem. See if you can get this. Then come back and I'll show you. Reversing the ratio of coulombs per gram, putting grams in the numerator and coulombs in the denominator, coulombs will cancel out and we'll be left with 9.1 times 10 to the minus 28 grams. That's really small. And that's the mass of the electron. But how are the electrons and the positive charges in the atom arranged? Well, it was first thought that there was a sphere of positive charge, kind of like a pudding, and embedded in that pudding would be little nuggets of electrons, enough electrons to balance the positive charge. And an experiment by Ernest Rutherford showed that this was not the case. What Rutherford did is to take a radioactive source that emitted alpha particles, that is, helium atoms stripped of their electrons, helium plus 2. So these bullets of helium nuclei were shot from the box toward a gold foil. Now, wrapped around the area around the gold foil was a fluorescent screen. And when alpha particles hit the fluorescent screen, it caused a little sparkle. What Rutherford expected to see was that the helium-ion bullets would travel straight through the gold foil because there would be no unbalanced forces acting on them, and they would hit the fluorescent screen directly behind the gold foil, causing a sparkle there. But that's not what he saw. What Rutherford actually saw was that while most alpha particles did travel straight through the gold foil, some were deflected at a very sharp angle that he did not expect, and a very few bounced back seemingly from the gold foil to hit the fluorescent screen in front of the gold foil. This was totally unexpected. Rutherford remarked it was like shooting a 15-inch shell at a piece of tissue paper, and it bounced back from the tissue paper to hit you. In the plum pudding model, the positive charges were so diffused throughout the atom that no strong unbalanced forces would act on the alpha particle to deflect it. But the strong deflections from the straight line path proved this to be incorrect. Instead, the experimental results supported a model in which all 79 of the gold atom's protons were located in a very small, extremely dense center of the atom. Rutherford called this center the nucleus. The electrons of the atom were in a diffuse cloud outside of the nucleus. With this model, most of the alpha particles would pass unimpeded through the electron cloud, but every now and then the path of the positively charged alpha particle would pass close to an atom's nucleus, and the dense positive charge of this nucleus would repel the alpha particle and cause its path to deflect from a straight line. And very infrequently, an alpha particle would be heading straight toward the nucleus and be so powerfully repelled that it would reverse course and strike the fluorescent screen in front of the foil. After Thomson's work, scientists realized that the atom was comprised of a positively charged particle called a proton and a negatively charged particle called an electron. Another particle was found in the nuclei of atoms, except hydrogen, in 1932. This particle was called the neutron. It has about the same mass as the proton, but it has no electrical charge. So, to summarize the masses, the electron's mass, 9.1 times 10 to the minus 28 grams. The proton's mass is 1.7 times 10 to the minus 24 grams, about 2,000 times heavier. And the neutron's mass is also 1.7 times 10 to the minus 24 grams. So the electron is about 1/2000th the mass of a proton or a neutron. That means virtually all the mass of an atom is derived from the protons and neutrons in the nucleus. Now, when we look at a periodic table, which has all the known elements organized in a very useful way, we might see, for example, iron represented with a 26 and then a 55.845. This is information you can use to determine the number of protons, the number of neutrons, and the number of electrons in the iron atom. So here is how you would go about doing that. The smaller number, the 26, is the atomic number. Sometimes you might see it written this way. In the periodic table you may see it this way. The way to distinguish the two numbers is the smaller number is always going to be the atomic number, and that's the number of protons in the iron atom. The larger number is the mass number, and you can round that off. We'll explain why it's a decimal, but you can round it off, and that will give you the number of protons plus neutrons in the nucleus. You now know the number of protons and the number of protons plus neutrons. You also know the number of electrons if the atom does not have an electrical charge, if it's not an ion. If it has all of its electrons, it hasn't lost or gained any, then the number of electrons has to equal the number of protons. They have to be the same number of negative charges as positive charges. So how can you figure out from this information the number of neutrons? Well, it's pretty simple. If 56 represents protons plus neutrons, and you subtract 26 protons, you'll be left with 30 neutrons. So this compound has 26 protons, it has 30 neutrons, and it has 26 electrons. Well, what if we did have ions? Here are two ions. One is a cation, iron 3+. It's called a cation because it has a positive charge. And then an anion, arsenic, and that has a -3 charge. So what I'd like you to do is pause the playback and see if you can come up with the number of protons, neutrons, and electrons for each. All right, this is how you would put this together. We did the iron already. It has 26 protons, 30 neutrons. But now the number of electrons, it's not the number of protons anymore because we have a +3 charge. You see that? So the number of electrons iron cation is going to have is going to be 26 minus 3. It's going to have 23 electrons. In other words, 26, the number of protons, minus 3. Now, arsenic is going to have 3 more electrons than protons. Because arsenic has 33 protons, then arsenic anion, As3-, is going to have 3 more electrons, or it's going to have 36 electrons. Now let's discuss the areas of the periodic table, a little bit of the nomenclature. The columns in the periodic table, going down, those are called groups or families. The organization of the periodic table puts elements that have similar physical and chemical characteristics in the same group or family, in the same column. Going across the periodic table, the rows are called periods. There are also certain regions in the periodic table: the metals, nonmetals, transition metals, and metalloids, and noble gases. The elements in brown here, in the first 2 columns, and then over here in a stepwise fashion, these are the metals. The nonmetals are in yellow here, as well as hydrogen. The transition metals are in red. The noble gases are the very last column in the periodic table. The group that tends to lose 1 electron to become +1 is the very first group: lithium, sodium, potassium, rubidium. The second group tends to lose 2 electrons: Be, Mg, Ca, Sr. And way over here, under 3a, we have metals that tend to lose 3 electrons, like aluminum, which forms a +3 cation, gallium, which forms a +3 cation, etc. It's the nonmetals that tend to gain electrons rather than lose them. So the element on the right side of the periodic table, with the exception of the noble gases, which don't interact very much, tend to gain 1 electron, 2, or 3. Group 7A, the halogens, fluorine, chlorine, bromine, and iodine, all tend to gain 1 electron to become a -1 anion. Oxygen, sulfur, selenium, all tend to gain 2 electrons to become a -2 anion. Nitrogen and phosphorus can gain 3 electrons to become a -3 anion. So you should definitely know these trends of loss or gain of electrons of elements in the periodic table. The metals tend to lose electrons, either 1 electron or 2 or 3. The nonmetals tend to gain electrons, either -1, -2, or -3, by gaining 1, 2, or 3 electrons. The way of organizing the elements in the periodic table, most of the credit is given to Mendeleev, a Russian scientist in the 1800s. And one thing that made his organization very useful was the fact that he predicted the properties of germanium before it was even discovered by organizing the elements in the periodic table the way he did. He organized them by atomic mass. We know now that you can get better organization using atomic number, but it was good enough to do what he did. He knew about silicon, silicon's properties, the mass of 28, a gray color, density of 2.32. It resists acid, resists base. Its oxide has a formula SiO2. And he knew the properties of tin, atomic mass 118, it's a white metal, density of 7.28, etc. From this, he was able to predict an element that had not yet been discovered, an element that was in between silicon and tin. The element turned out to be germanium, and he predicted a value of atomic mass for it of 72. The measured value is 72.6. He predicted a gray color for it. It was gray-white. He predicted a density of this unknown element of 5.5. After its discovery, it was 5.4. And he predicted that it would be resistant to acids and bases, and it was. And he predicted the formula of the oxide. So this was a very great success, and it illustrated to everyone why the periodic table is so fantastically useful to chemists.